Hi to everybody watching this video. I wanted to really put this video together. It's asking a question, do black holes experience length contraction? And I want to address an idea I had. It's a little bit of a theory of my own, but it has foundations in relativity. I've not been able to find it explained like this anywhere else on the internet. If you know of an explanation like this, please leave it in the comments. I welcome it. But right now we're looking at a graph. I just posted a video recently called Are We Always Traveling at the Speed of Light? That kind of explains what we're seeing here. But for anybody that just wants a quick synopsis of what the video is explaining, it was saying, okay, here's a time dilation graph, what we typically see and how we get it into this, what you see here. So here it is. We have the y-axis, that's time change, and then we have the square root of 1 minus x squared over 1. So x squared is our velocity, and 1 right now is our normalizer for c. We're making the speed of light equal 1 in this graph. So that's aligning to the Planck units and really normalizing the graph. You could see here that it kind of aligns to a circle, and I'll explain what we're looking at. So right now, d at the bottom here, this is our velocity through space, and c is where we are as observers seeing people traveling at d, the speed here for d, how much slower time is moving for them. So as I move a, you can see, okay, they are going 0.66 c. And for every second I'm experiencing as the observer, they are experiencing 70.75 seconds. So their time is going slower. And the vectors together, for time and space, always equal c. So no matter what, through space-time, you're always moving at c. That's what the last video answers. So I think that's pretty interesting. But now to address why the black hole question that I had earlier. Do black holes experience length contraction? So just like I explained for time dilation, the same thing works for length contraction. If I'm moving at 0.68 c right here, c being the speed of light, length gets contracted to 73% of its original length. So now going into my next graph, it looks similar, but I'm adding a few elements to it. So right now, we are looking at a black hole through time. So a black hole with radius 0.1. If you go forward a second, it still has radius 0.1. So through time, it looks like this cylinder, this black hole cylinder. Now, that takes a little bit of thinking to get to, but really, it's almost as if you did a long exposure on a photograph and you run across a screen with a light, you'll see a line for that light rather than a point. So the same thing with a black hole through time, you're going to see a cylinder since a black hole has radius. So right now, we are looking at a black hole with radius 0.1 on the same graph that we were just looking at on the other tab. This is a black hole at rest, and so it's just going through time at c, at the speed of light. So now if I tilt this axis on its side a little bit, it's hard to see here, but let's go back over here. You can see we have the same formula where we are going at 100% of 1 for 1 second, zero. This is our zero spatial motion. We're not going anywhere spatially, so we're going all the way through. All of our motion is through time. So now if I grab point A and I start moving this, you can see, okay, same thing. I'm going 0.2 c, and now time is dilated to 0.98 seconds for every second I'm experiencing, but the same for length. So length is 98% of the original length for 0.2 c. But if you look down here, this is our Schwarzschild radius. So I'm going to take this point and move us faster through time. And as we move faster through time, let's see, you can see that it turns elliptical. So we are starting to get a further radius in the direction of motion. So our spatial direction, we're starting to have a black hole that's looking a lot more like an ellipsoid than a sphere. So what does that mean? All right, well, I have this point Q here that's telling me my radius in that X direction. So now I'm going to ignore the negative, but it is 0.29 when I had an original radius of 0.1. So if you take 2.9, all right, how do we get it back to 0.1? So I've got a black hole that's actually not experiencing length contraction, but actually getting longer as its speed grows faster. So going back to the top here, we are going 0.94 c, so fairly fast, almost the speed of light, and our length went from 0.1 to 0.29. But at the same time, our length contraction is 0.34 of the original one that we were going. So for every meter that we were in length, now we're 0.34 meters. So if we take 0.34 and this 0.29, well, if we do 0.34 times 0.29, we end up back at 0.1. And so the length contraction offsets our length growth that we would have spatially, back to 0.1. So our radius always maintains 0.1. So to answer the question, do black holes experience length contraction? Yes and no. They have length growth offset with length contraction, which keeps us at our original black hole Schwarzschild radius. Anyway, let me know if you have any issues with this, or if you've seen it elsewhere on the internet. I'd be very interested in reading this. Let me know. Leave your comments in the comment section. Thank you. Bye.